Introducing NAVYA's Autonomous Mobility Shuttle project, the first of its kind. NAVYA's vision is to revolutionize urban transportation with fully autonomous electric shuttles that are safe, sustainable, and accessible. Since its launch in 2014, NAVYA has focused on developing innovative, eco-friendly mobility solutions that help reduce congestion and emissions. In 2016, NAVYA deployed its first shuttle, the Arma, in various global cities like Lyon and Paris in France, Las Vegas and Michigan City in the USA, and Christchurch in New Zealand. These shuttles are level 4 autonomous, meaning they can operate independently without any human intervention. They are equipped with an array of sensors, including GPS, LiDARs, stereo vision cameras, and odometry, which enable precise navigation. The symmetric design allows for bidirectional movement, similar to what we discussed in our Zooks episode. The focus really over here is on passenger safety, comfort, and reliability. Engineered to operate on existing urban infrastructure, the shuttle reaches speeds of up to 28 miles per hour or 45 kilometers per hour in urban and suburban settings. With a capacity for 15 passengers, sensors like LiDAR and cameras ensure high reliability for obstacle avoidance. NAVYA has named this model the NAVYA Arma, which currently operates across cities worldwide. Looking at global deployments, NAVYA operates at the NTU campus in Singapore, where the shuttle offers 24/7 service to students and faculty members. This fully autonomous shuttle service in a closed campus setting demonstrates NAVYA's commitment to provide safe and reliable transportation for universities and closed campus institutions. NAVYA has also made strides in Europe, operating autonomous shuttles in France and Switzerland for several years. This fleet highlights NAVYA's growing role in shaping the European mass transit system. And it doesn't stop here. NAVYA shuttles have been deployed in airports worldwide, aiding in seamless passenger and cargo movement between airplanes and the terminals. The potential for these shuttles spans from urban mobility to closed campus transit solutions. That brings us to this question: when did this project start and how did it evolve? In 2014, NAVYA was founded with a vision to create autonomous, sustainable transportation solutions that would redefine urban mobility. By 2015, pilot testing began in Paris, providing critical insights into how autonomous shuttles operate within dense urban settings. These early tests were invaluable in collecting feedback from the users and identifying the unique challenges of urban navigation. In 2016, NAVYA launched its first shuttle in Lyon, France, and soon after expanded to Sion, Switzerland, making its debut on the public roads. These deployments established NAVYA as a forerunner in public autonomous transit, demonstrating that autonomous shuttles could reliably navigate open road environments and interact safely with everyday traffic, providing passengers in Switzerland a robust mode of transportation. The following year, NAVYA brought its technology to the US, participating in the AMCITY project at the University of Michigan. This opportunity allowed NAVYA shuttle to be tested within a controlled urban environment, complete with mixed traffic scenarios. Here, NAVYA fine-tuned its navigation mechanism, vehicle-to-infrastructure communication, and gained insights that would support real-world applications on a larger scale. In 2017, NAVYA extended its reach to Singapore, launching a campus shuttle service at NTU that provided students and faculty members with seamless mobility across campus. This deployment highlighted NAVYA's adaptability in a closed pedestrian-heavy environment and set the stage for future campus-based applications worldwide. Today, NAVYA is focused on scaling its operations globally, adapting its shuttles for diverse settings like industrial complexes, airports, and urban mass transit systems. With projects across continents, NAVYA continues to refine its technology, paving the way for a future of fully integrated autonomous mobility. From its initial launch in Lyon, France to Lake Nona, Florida, NAVYA has expanded its footprint in the global urban landscapes. And from tourist attractions in Singapore to the campuses of the European Space Agency in the Netherlands, NAVYA is expanding its footprint at the speed of light. With an established footprint across the world, NAVYA is transforming how we think about autonomous mass transit. But the real question is, how does this shuttle work? How does it make those navigation decisions? It's the self-driving system that helps it make those decisions, and it includes four key components. First up, we got perception, basically the eyes of the vehicle. Data from sensors such as cameras and LiDAR is fused using this module to develop a coherent view of the surroundings. This allows the vehicle to detect objects, pedestrians, other vehicles, and stop signs. The data from the perception module is then fed to the localization module. This serves as the compass. Data from GPS, IMU sensors, and LiDAR is combined with the detailed 3D maps to identify the vehicle's exact location. Now that we know where we are, we still need to determine the route. That's where the Path Planner comes into play. Path Planner uses detailed 3D maps along with sensor data to create safe and efficient trajectories to destination. Finally, these trajectories are executed by the motion control system, which activates steering, accelerator, and brake. Those are the four key components of the self-driving stack. Here is how NAVYA actually implements these functions. Before we dive deep into this stack, we wanted to let you know that we cover this technology and similar case studies in great detail in our course on self-driving cars. From Zoox to Waymo and Tesla, we break down the tech stack of these vehicles in an easy to understand manner. Ready to start your journey in this field? Check the link in the description below. Now let's get back to NAVYA. Now that we have covered the high-level overview, let's take a look at the detailed tech stack of NAVYA. So this is the system architecture of the NAVYA's autonomous shuttle, commonly referred to as NAVYA Drive. At its core, it comprises of three primary modules on the top, working with the three satellite modules located below to enable autonomous navigation. The three primary modules, namely perception, decision, and action, these are the core modules that work together to allow the vehicle to perceive its surrounding, identify its location, plan a trajectory, and execute these commands in real time. Surrounding these three are the satellite modules like the cartography, human-machine interface, and simulation. These three satellite modules strengthen the system's reliability and elevates the user experience. Let's decode these modules one step at a time. The first module in the NAVYA system is the perception module. This module combines our standard perception and localization components. It is designed to generate a 3D view of the shuttle surroundings and track its position with high precision. The perception module enables the vehicle to understand its environment, detect obstacles, and anticipate movement. By collecting and processing data from various sensors, the system actually creates a complete real-time 3D picture of the shuttle surrounding. Now let's take a closer look at the sensors that enable this module. Starting with LiDAR, the shuttle is equipped with both 3D and 2D LiDAR systems. LiDAR works by emitting laser pulses that bounce back from objects around the shuttle. By measuring the time it takes for each pulse to return, LiDAR calculates the distance and the shape of the objects in the environment, allowing the shuttle to recognize obstacles with remarkable accuracy. Next, we have cameras. NAVYA shuttles are equipped with a range of high-resolution cameras capturing detailed images of the surroundings. These cameras allow the system to identify objects, cars, pedestrians, traffic lights, and more, enhancing the shuttle's environmental awareness and adding an additional layer of detail to the perception process. With data from LiDAR and cameras, the perception module uses sensor fusion algorithms to integrate and interpret these inputs. By combining the strengths of all of these sensors, the system builds a coherent 3D view of the environment day or night. There are a range of algorithms that can be used to fuse the sensor inputs, and we cover this in detail in our course. That brings us to localization. How does it know its location? The localization component of the perception module is what allows NAVYA to pinpoint its exact position, orientation, and speed. It consists of GPS, odometry sensors, and LiDAR. Using techniques like map matching and sensor fusion, by combining the data from LiDAR, GPS, and other sensors, the localization module merges data to provide precise positioning even in complex or GPS-challenged environments, enabling the shuttle to navigate safely and accurately. One thing to remember here is that in the world of self-driving cars, we need centimeter level accuracy, and hence the need for multiple sensors because GPS only provides meter level accuracy, which is not sufficient for self driving. NAVYA system also includes V2X or vehicle to everything technology, enabling communication with the nearby traffic lights. This sensor allows the shuttle to understand the status of nearby traffic lights, anticipate changes, and optimize the routes in real time in these urban settings, enable safe and efficient trajectories. In addition to VTX, the shuttles are also equipped with telecommunication modules for robust communication between the shuttle, infrastructure, and servers located in data centers. This feature also enables teleguidance in situations that may exceed the shuttle's autonomous capabilities, such as complex or unexpected road conditions. So, using data from all perception and localization sensors, the NAVYA system creates a comprehensive real-time map of its surrounding while constantly tracking its position. This output from the perception module is then passed to the decision module, which formulates the safest and the most efficient route for the shuttle. Here is a short snippet that shows the obstacle detection performed by the perception module. NAVYA here uses LiDAR, camera, GPS, odometry, and IMU sensors to detect, track, and classify obstacles, ensuring the shuttle can respond dynamically to its environment. The perception module processes billions of data per second, tracking the speed, shape, and position of nearby objects for safe navigation. Here we can use state-of-the-art object detection systems such as YOLO or SSDNet. Here is another snippet showing the localization function, which uses data from perception module to continuously track the vehicle's location at airports and campus sites. Here, typically a map matching technique is used to identify the precise location of the vehicle. This data is then fed to the decision module. The decision module is the core of the NAVYA's autonomous system, responsible for planning the shuttle's journey from start to finish. By processing inputs from the perception and localization module, the decision module evaluates safe and efficient routes and continuously adjusts speed and direction in real time, ensuring a comfortable and secure ride while adapting to the environment. The decision module begins by calculating a safe and efficient route using real-time sensor data and high-definition maps provided by the perception and localization module. Once the general route is set, it refines this into a detailed spatial and temporal path, factoring in inputs from obstacle detection and localization functions to adjust speed and trajectory. Here we can use numerous algorithms such as finite state machines, decision trees, and more. This step-by-step planning ensures the shuttle navigates smoothly through varying environments, keeping passenger safety and comfort as priorities. The finalized trajectory is then sent to the action module, which translates it into precise vehicle movements. The action module executes driving commands controlling speed, steering, and brakes. It translates the trajectory planned by the decision module into precise vehicle movements, functioning as the conductor that synchronizes all the components of the drive system to maintain stability and safety during operation. That covers the three core modules of NAVYA's autonomous shuttle architecture. In addition to those three core modules, there are three satellite modules that aid in autonomous navigation, and those are cartography, human-machine interface, and simulation. Now let's cover each of these one by one. To ensure precise navigation, NAVYA Drive relies on the cartography module, which provides high-definition 3D LiDAR maps. These maps allow the shuttle to verify its position and analyze its environment in real time, comparing real-world sensor data with pre-mapped environments. This precise positioning and environmental awareness is essential for safe and accurate autonomous operations across complex sites. The Human-Machine Interface or HMI is designed to simplify interactions for passengers, operators, and maintenance personnel. By providing intuitive sound and visual cues inside and outside the vehicle, the HMI makes the user experience seamless. This model prioritizes clarity, helping passengers feel informed and safe while enabling supervisors to monitor the system easily. A key component of this module is the Fleet Management Dashboard. This dashboard enables operators to monitor the autonomous fleet deployed across hundreds of campuses remotely and in real time. To enable safety and performance, NAVYA integrates a simulation module that enables extensive virtual testing of the NAVYA drive software components. This module allows for iterative testing and refinement, reducing the need for real-world testing. By leveraging operational data gathered since 2015, simulation helps NAVYA continuously improve system efficiency, performance, and the autonomous navigation stack, thereby enabling high levels of safety standards in a controlled environment. So, here is how it all comes together. The process begins with site analysis, where the team examines the geographic and landscape details of the location selected for shuttle deployment. This analysis includes gathering customer specific requirements such as preferred routes, speed limits, and other operational parameters to ensure the solution meets their needs. Once the detailed information is collected, the team moves into the mapping phase. Using vehicle mounted sensors like LiDAR and GPS, they map the entire site, creating a detailed 3D representation of the surroundings. The goal really is to provide a comprehensive view of the environment to support precise autonomous navigation. In this phase, the team applies machine learning algorithms to identify and annotate static objects on the map, such as traffic lights, stop signs, and road markings. This post-processing minimizes the need for dynamic processing during operation. The result is a highly detailed HD map that includes essential site information, speed limits, signage, road lanes, and more that the shuttle will rely on for safe navigation. With the HD map and real-time sensor data, the shuttle is now ready for deployment. The autonomous navigation system uses this detailed map along with the live sensor inputs to make decisions, guiding the vehicle smoothly from its starting point to its destination on site. This is where the full system architecture we discussed today comes into action, bringing the entire process to life. NAVYA operates at Michigan's M-City, a 32-acre test facility designed specifically for autonomous and connected vehicle research at the University of Michigan. This facility features 5 miles of roads with urban infrastructure elements including simulated intersections, crosswalks, roundabouts, and building facades. NAVYA's autonomous shuttles undergoes rigorous testing here to evaluate their capabilities in navigating complex urban settings. The M-City environment includes real-time traffic signals, pedestrian simulators, and varied road conditions, which provide NAVYA shuttle with dynamic scenarios to test obstacle detection module, precise localization module, and adaptive path planning. Insights gathered from these tests are pivotal in enhancing shuttle safety, responsiveness, and reliability. NAVYA's autonomous shuttle operate in high-density urban settings in Paris, La Défense, and across Lyon, France, serving as efficient last-mile solutions in bustling business districts. In Lyon, the shuttle runs on 1.3-kilometer route connecting major transit points, while in La Défense, they navigate a pedestrian-heavy environment with complex traffic patterns. These refinements allow NAVYA to refine key navigation systems as shuttles adapt to unpredictable urban challenges. The data and insights gathered here have been crucial in enhancing the shuttle's performance in real-world high-traffic scenarios. In Sion, Switzerland, NAVYA shuttle marks one of the first autonomous deployments on public roads covering urban and semi-rural routes with varied infrastructure and elevation changes. This deployment provides essential insights into the shuttle's adaptability, testing NAVYA's high-definition mapping, sensor fusion, and precise localization in mixed-use environments. The Swiss deployment has helped improve NAVYA shuttle response to open road conditions, optimizing performance for diverse settings, and advancing the technology for future public road implementations. NAVYA shuttles operate on numerous private sites, university campuses, and airports, providing safe, zero-emission transportation tailored to each environment. On campuses and private sites, the shuttles navigate pedestrian-dense areas, testing adaptability to different layouts and restricted paths, while airports introduce the added complexity of high passenger flow and multi-terminal routes. In these settings, NAVYA leverages high-definition mapping and GPS-enabled autonomous navigation system, enabling the shuttle to handle dynamic elements like traffic signals, crosswalks, and unexpected obstacles. We cover this technology and similar case studies in great detail in our course on self-driving cars. From Zoox to Waymo and Tesla, we break down these stacks in an easy-to-understand manner for you. Ready to start your journey in this field? Check the link in the description below. Thank you.